So now we are pretty much a professional grapher. We know how to take slopes, we know how to take areas, we know how to do hopefully everything. We're going to try to put it all together. As a little reminder here, we know that if we take the slope of a dt graph, we get the velocity, and if we take the slope of a velocity graph, we get the acceleration. Which means in practice that if our dt graph is curved, we take the slope, we're going to get a diagonal line. Okay? And if we take the slope of a diagonal line, we're going to get a horizontal line. And if we take the slope of a horizontal line, we're going to get 0, a horizontal line at the 0. So that's just a little reminder of how this thing is going to work, and we're going to take a look at a big position time graph. So here's a big dt graph. The first thing you want to think about is how many different sections are there. I want to break this into sections. The first one is pretty easy. I'll break it up here. I think it's pretty clear that something of interest is happening here. Now here it's a horizontal line, and then it starts curving up. So that's another spot where we're interested in. The curve, though, right about here, becomes the straight line. So that's another region. The straight line starts curving here. So that's another region. Curve, 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 curve. Suddenly the curve becomes straight over here. There are at least 1, 2, 3, 4, 5, 6 distinct regions on this graph. You might even put 7. I think a lot of you realize that something interesting is happening here right at the top. So I'll add that. But I think you'll see as we go on that it's really nothing actually special that's happening there. But let's figure that out. So taking a look at the first section, we can see that the dt graph is straight. We know that means uniform motion, constant velocity. So none of us are surprised, hopefully, that the velocity won't change during that section. We find the slope of the dt graph, and we know it's going to be a horizontal line. Let's say I did the slope and I found that it was 2. Well, then there'd be a horizontal line here at a value of 2. Simple as that. Taking a look at the second section, I can see, without doing any math whatsoever, that the slope is clearly 0. So this is a bit weird. The graph is going to suddenly drop to 0. And I can make this a dotted line. That's not very realistic, of course, because of the sharp line, but we'll talk more about that later. It starts curving. The curve is going to give us a diagonal line. The slope at the beginning of the curve is clearly 0. A little bit later, it's got a slope of, say, 1. A little while later, 2. It's increasing. So I know it's going to diagonally up. But if I skip it for 1 second and I look at this section, I can see that this section has a slope of about 4. So if this is 2, this is 4. And this curved section has to be straight, so I'll just connect those two. So far so good. The velocity was constant, then the velocity was 0, all of a second, which is weird. Then the velocity increased to about 4, and it stayed there for a while. What's happening now? The curve is going down. So the slope is, say, 4. Here the tangent is clearly going to be 0. There it's going to be negative. At the top, the velocity is 0. And if I grab my ruler, I know where to put the line. So the curve becomes a straight line. Then the last section, the slope is constant. I know what number it is. It's whatever this number is. It's going to stay at that level until the end. So there's my VT graph. Again, all we cared about was the slope. The slope of this was about that. The slope of this was 0. Slope increased until the slope was about 4. Then the slope decreased till it was 0. And then the slope became negative, and then it stayed negative. It's just a graph of the slope of that graph. Finding the AT graph from the velocity time graph is the exact same thing, but generally easier. What's the slope for the first little bit? It's clearly 0. What's the slope for the second bit? It's clearly 0. What's the slope for the third part? It's clearly positive. What's the slope for this middle part? Clearly 0. What's the slope for this whole section? Negative. A little steeper than over here, so it'll be a little lower. And what's the slope for the last bit? Clearly 0. I can connect these little gaps with a dotted line or a solid line, it doesn't really matter. And for those of you who are wondering, clearly when the velocity went from 2 to 0, something had to happen. So it's not realistic just to say A was 0 the whole time. It's okay. Really, technically, there must have been some very short negative acceleration to stop this guy. But again, it's not realistic to stop in 0 time. And now we have our acceleration time graph, our velocity time graph, based on this displacement time graph. Now that we have our acceleration time graph, though, maybe we should take a second and just make sure that we're actually understanding what's going on. If this velocity time graph represents the same motion as this dt graph, then let's describe the motion and just sort of make sure. For this first region here, the object has a straight dt graph, which means that every second they're changing their position at the same amount. Uniform motion. So the object goes at a constant speed in the positive direction and then stops all of a sudden for a while and stays at this position. The object all of a sudden accelerates, starts going at a constant velocity, stays there for a while, slows down, stops, backs up, and keeps backing up until it's back at the original spot. That's what the graph says. What does the velocity time graph say? The velocity time graph says the object was going at a constant velocity in the positive direction, all of a sudden stopped, accelerated in the positive direction, and then it stopped, then it maintained that speed for a while. Then it slowed down, turned around, and then maintained a velocity in the negative direction. Well, which is hopefully exactly what I just said for the dt graph. So that's really good. The two are lining up. Another thing we could point out, if we were inclined to take the area of this box, the area of this trapezoid, would have to be the same as the area of this shape. Because we know this area plus these two areas would have to add up to 0, because the object's total displacement, looking at the dt graph, is clearly 0. It started at 0, it ended at 0. So this area plus this area minus this area, well, this area is negative, right? Will add up to 0. And the AT graph should say the same thing, but it has a little less information even. Look, the AT graph just says this thing wasn't accelerating for the first 2 sections. Well, that's true. It's just not very specific. Then the AT graph says it was accelerating in the positive direction for a little while. We already said that. Then it stopped accelerating. Then it accelerated in the negative direction for a while, and then it stopped accelerating again. So the AT graph describes the motion as well, but it doesn't give us as much information. And that's going to be important when we try to go the other way, to take an AT graph and turn it into a VT graph, which I believe is in the next video.